for resistance and temperature, there is a temperature dependence on resistance. And I'll help you make sense of this. Now, what is actually getting in the way of electrons is collisions. It will collide with atoms, other atoms, and that slows down their progress. Okay? So let me ask you this. If collisions are, let's say in the morning, in the hallway, everyone's pretty comatose and moving very slow. It's very easy to dodge your other students because they're moving so slow. 7th hour, everyone is caffeined up and they're psyched about getting out of school and they are going crazy. They're running around, they're pushing their friends, they're bouncing everywhere. Which is easier to get through the hall? Where the students have low energy and there's fewer collisions, or when they have high energy and you're constantly running into people? The low energy situation is easier to get through. Similarly, if the molecules are moving faster in a substance, like in a hot conductor, it is harder to get through. Resistance is proportional to temperature. So here is our relationship right here. Now we use it. Typically we have a resistivity relationship. The resistivity is some standard value at a standard temperature. Usually we use for T naught, we use 20 degrees Celsius. Why do we use 20 degrees Celsius? Room temperature. So rho naught is the resistivity of a metal at room temperature. When you look up the resistivity, it's typically rho naught, the resistivity at room temperature. You multiply that by, this factor is 1 because you need a 1 in there to get your initial resistance there, or your initial resistivity. And then you multiply it by this. This is called the temperature coefficient of resistivity multiplied by the temperature difference from T naught, which is typically 20 degrees Celsius. The temperature coefficient of resistivity, one way to look at that is this is simply the fractional increase per degree Celsius change. Now you can use Kelvin or Celsius. Whenever there's a change in temperature, like right there, doesn't matter where you use Kelvin or Celsius because the changes are always the same. So if this is equal to, for example, I'll give you, this would never really occur, but if the alpha was 0.1, that means the resistivity increases 10% for every degree temperature increase. It would never be that big, but that's a way to get a conceptual handle on it. If this were 0.1, that means for every temperature, every increase of 1 degree, the resistivity goes up by 10%. That would never happen. More likely, it's in like the fraction of a percent. By the way, you can do the same thing for resistance. Resistance equals R naught, but that depends on the material size and length, times the same thing. You can do, it would have resistance R naught at T naught. You can do the same thing with resistance or resistivity. An example is this. Platinum has resistance of 50 ohms at 20 degrees, a sample of it. Notice that you can't say platinum has that resistance, depends on the shape. But if it's a 50 ohm resistance at 20 degrees, when immersed in a melted metal, the resistance is 76.8 ohms. What's the temperature of this melted metal that I immersed the platinum in? Well, you use this equation right here. To find our resistance, all we're going to do is I just multiply this through like that. You can solve for delta T like this, and quickly moving through this, the alpha for platinum, you can see this is a really small number. It's 3.92 times 10 to the negative 3, so it's 1,000th, 3.92 thousandths per it, and it's measured in per degree Celsius. Notice that C in the negative 1. Multiply that by the R naught, and you can see that when you do all the math here, you get 137 degrees Celsius. So that is the change in temperature. So my total temperature is the initial temperature plus our change. We started at 20, you add 137. 157 is the temperature.